Okay, strategies. First thing, you use CPD radar when troubleshooting flat, elevated noise floors on a node, or when SNR on all the upstream channels is reduced. You go to the fiber node and you start there. Identify the output leg that is carrying CPD signal of your interest. Each leg can have some different CPD, but you'll identify it by its time delay. Then you go to the next split point of the network on that leg. And if there are more split points to go through, you verify the signals at next split point. Continue and repeat until you are on a straight leg to the CPD source and test again one span before expected CPD source location. For those who are interested in more detailed description, how to act, here is the flowchart. I know you want to laugh, and that was the purpose for this. So it's not that complicated, it's simple. When you understand what is on the CPD radar screen and how to adjust things, you'll be good to go and find all the problems that were remaining on the network for a long time. So we see here a plot showing two CPD sources. Again, here is time delay, here is level. One peak, other peak. The marker goes automatically at top of the max peak, and the delay range up to 25 microseconds, as here, will be typically enough in all situations that you will be in. This is allowing to scan up to 10,700 feet distance of an average coax cable. And it goes through the amplifiers. So if you've got a node where coax can be longer than 10,700 feet, you will switch to 50 microseconds. But remember that delay range is not changing resolution. It's still the same. Resolution will be changed when you use zoom, and that will be used when you need very precise measurement, and you need to check if there is just one source or two sources hidden in one peak. The bandpass filter here, you can change the minimum and maximum to select the bandwidth that is less affected by CW-like peaks in the upstream. I'll show that in the movie later. Noise suppression is something that helps to reveal these peaks from noise if the noise floor is hiding them. It's like at -50 here or -45, you would see this peak, but this one would be hidden. So you can switch from standard to high. You can change marker option from automatic max to move it left, right, or jump between the peaks. Meters and feet, depending who likes what, you can change this setting in the general settings of the meter. There is a return spectrum analyzer on the Quiver that helps in finding out what is the upstream level at the test port where you are connected, and if there is any upstream visible. Test ports can be broken, and if we don't see any signal at the input of the radar, it will just show flat line without peaks on the noise floor. And you might think there is no CPD, but actually there is no proper connectivity to the return or to the forward, because the forward is also important. This is average level of what you will see at the test ports. It's like -10 dBmV. Please remember that return levels are lower than what you would expect at the test board, because these test boards were not meant to measure the return level. You've got forward test boards to measure the forward level. You are most interested in that, and you've got typically a sweep insertion port, which is also different purpose. Here we need to look at the level of the signal. If it's -10, it's okay. If it's -20, you may use the Q amp that will boost the signal. We'll explain in a moment what to do with it and why. Here is relatively high CPD level visible already in the spectrum, but from the spectrum we don't know if this is just one source or these are two sources. But CPD radar will show up and it will give us answer. There are two peaks. Most likely this one is causing this elevated noise floor, or it may drop slightly and you will need to find this one as well. Here is low level of CPD visible in the upstream plot, but on the CPD radar you can see that in zoom mode that is showing from -2 microseconds to +2 microseconds around the position of the from the position of the marker. There are two CPD peaks and a little one here. When checking connectivity, you can verify with existing SLM the forward signal level. Forward signal level is not that important for the levels displayed as a CPD peak, but this reference should be between -10 +15 dBmV. It can be -15, not that big problem, but if you've got amplifiers with 50 dBmV output and there are 20 dB test boards, you might need to use 20 dB pad to avoid overloading the input circuitry of the Quiver on the forward input port. Some Quivers will not have a problem with this, some might. Upstream signal level, if it's coming up to 0, it's perfect. If the max hold, this pink line, is at -10, it's absolutely enough to search for CPD without additional amplifiers. If it's -20 or less, then use the additional amp. I know that the technicians don't really have nowadays access to the hub, but there are people who do have and who can have also a Quiver and help other technicians to save driving and time, because when someone is troubleshooting intermittent CPD that was very high level at night, and now in the morning when he goes to work, this event is not present, it's just slightly elevated noise floor. Searching for CPD is possible, but when you are 10 miles away from the fiber node, before you drive there, you can verify if it's present and it's searchable. You can connect Quiver at the hub to optical transmitter RF test board and to the return signal test board on the optical receiver of a particular node and run a scan that will reveal CPD information there. If it displays that there is CPD, then you can go and you will find it. If there is nothing displayed, you can save 10 miles one way, 10 miles other way or someplace else. How to do this? We'll show in a moment on the movie. The Quiver can scan up to 17 miles one way. And in second mode, this distance is twice longer. Doesn't want to start. Okay, started. So first we are checking upstream signal level. In the max hold, the tops of ST QAMs are reaching 0 dBmV, which is perfect. We activate CPD Radar. This is in older firmware version, passive. It starts in 25 microsecond delay range. Now we will extend this delay range to 200 microseconds. That allows us to see the peak from very long distance. It was tested in Europe at that time, and it was 21 kilometers. So we could do this from a distance, verify if it was there. I said something about amplifier. We have in the Quiver kit Q-amp. It's a device that is offering 20 or 30 dB gain. We prefer to use 20. It's 9-volt battery powered. It lasts for a long time, like forever. It's activated with just one switch. You switch between gain. It will automatically power off after like 6 minutes. So whenever you are using this device, remember that it has auto off feature. You connect it like this. From the device, you connect to the RF in, and from RF out, you connect to the Quiver return input. Then you activate with this push button. There is next to that button an LED that is showing which gain is actually used. If you push it again, it will switch to 30 dB, but we prefer to use 20 dB. 30 is not necessary, at least not always. If the Q-amp is powered on, of course it has gain, and it filters everything above 40 or 70 megahertz, depending on the design. It filters out this upper part of spectrum. When it powers down, it passes entire bandwidth of the return and applies around 4-5 dB in insertion loss. So remember about it. If it powers down automatically, you may not see the peaks, or you will see them much lower. Make sure it's powered on and proper gain is highlighted when you intend to use it. But depending on the device and on the plant, if you typically see CPD properly and you search it comfortably without usage of Q-amp, work without a Q-amp. If you feel like you have to use it, you have to use it. Just pay attention to the fact that it needs to be powered on when you want it. Here is an example how this Q-amp helped us in finding low-level intermittent CPD source. This CPD was bothering node for months, and at the time of search, it was very low level. We came to the fiber node, connected the meter. The level at the test port was reaching in max hold only minus 20 dB. You can see it here. To match the levels with the monitoring systems there, we were missing 20 dB. And we've applied this 20 dB. The signal was boosted. You can see that tops of the SC quamps are reaching 0 dBmV, and we were able to reveal these two low-level peaks. They are repeatable after each scan in the same place. These are the CPD sources. Take a look. This one is minus 55. If it was 20 dB down, it was minus 75. It was like one of these blips here. And this one was not visible at all. Here we revealed them and we traced the CPD source and fixed the problem. And it was not back. I promise that you will be able to troubleshoot without disconnecting network. One of the tools for this is our test probe, which you are putting into the seizure screw port of a tap, or you can also use an adapter and put it on a 90-degree angle connector as well. QDP20 is here. It has two outputs. Each is full band 20 dB attenuated test port, bidirectional with really high isolation between the ports. This probe is power isolating and it does not influence the signal return loss, the tap return loss or the frequency response. It has really good parameters. This one will not affect the signal such the CPD will be gone. You'll be able to measure it and to trace it. The two other examples are devices that not very often you will see. They are Canadian taps and splitters by Lindsay, but we've got probes for this as well. There are some other probes available in our portfolio too. When you are starting at a fiber node, the first thing you will check is how the network looks like. You need to understand where what goes, where are these legs going, and find out if this node has a test port after the return amplifier. If it does have after return amplifier, then it's very comfortable to work with because we connect the forward to the forward test port, and the fiber node can have different sides. So if different sides are fed by different forward signal, make sure that you always use the forward signal and the return signal from a particular section of the node. So here we are connected already with forward, and we begin testing from connecting to combined return test port after the amplifier that is carrying information about CPD coming on all these legs. So we'll see them all. And here is the result. We see two CPD events. One is small, one is higher. So they can be coming on one leg, but they can be coming just one on the second one. Here is something important. This is the level. When we go to these legs, the level will drop by the insertion loss of the combiner and the gain of the return amplifier. So we connect to one leg, we test, and we see nothing. We might want to increase the time delay range in case we work in long distance nodes. We connect to the other port, it's not there. We connect to a next port, and we see, of course, lower level, but still at the same time delay, almost exactly same as we were seeing here. And this is our main peak. It's coming on this leg, on this one. If we test the last leg, we see nothing. On the initial picture, we could see one more peak here. We don't see it in these conditions because the gain of the amplifier and insertion loss of this network here caused it to be simply here. If you are very much interested in tracing all of them, you can use the Q-amp to boost the signal. Connections at the amps are similar. There is a better chance that at the amplifier there will be a suitable test port carrying at the spot carrying all the upstream signals. So again, we connect to the forward test port with the forward. We check combined return. We check which leg, 1, 2, 3, and if we find nothing, but at the fiber node there was something, then either we are at a wrong spot, or make sure that you see properly forward and return signals if the test ports are good. So if you found that on one of these legs there is a problem, just follow it down to the next split. When connecting at the passives, you use QTP20 test probe that you put into the scissor screw access port and get the signal straight from the scissor screw. So when testing at a splitter, at a split points, always do this. Connect on one side and verify if there is anything visible. Let's say CPD signal is coming on the other leg, but take a look what you will see. You will see here small CPD peak because isolation of these two ports very often is not that high. So you can see the CPD leaking here. It will be small bleep, sometimes larger, but if you test on the other side, you will see that this peak will be at the same time delay, but much higher. And this is the correct direction to go after this CPD. So remember at the split points to test both sides and follow the large peak, the largest at the same time delay. There are some tricks that you will use when troubleshooting from cabinets that are densely populated, stuffed with devices, and you can't access ports, or some ports are broken. For example, on the active is broken return port or not present. You connect to a test port for the forward at an active, and you can connect return to the nearest passive after the active if they are in the same cabinet. Use the QTP20 probe and you will get indications. End of the line. If you find yourself at the end of the line and you will be seeing some CPD, this means that there is something wrong. The signal level of the forward is typically too low at the tap output to trigger the CPD source to generate that noise. It needs to be in the distribution network. On the drop line, it will not manifest itself with noise. But if you see the noise, this means that there is an amplifier in the house or in the MDU. I was telling you about a need to range the CPD source from a preceding device. For one of the reasons is that when you put a ladder on the cable and you shake the spans, one span to the left, the other span to the right, you can simply cause vibration on the devices where the CPD is located. If this is just a loose connector, it might cause the CPD to go away for some time. So don't try to range CPD down to the 0 point. Always check from the preceding devices group. If it's at the next, go simply to the next. Verify cables, connections, loose connectors, seizure screws, all of them. Here is an example of what may happen if you are at the amplifier and you see and there is either a fault right after the amplifier or exactly at the output port. The CPD will be indicated at 0 of the time delay. This time delay can be also indicated as negative value, slightly between -1 and 0. That's nothing wrong. There are some time delays related to the diplex filters inside of the device, and Quiver is calibrated to allow to see these details. The amplifier itself can generate some CPD-like level. This is the second order intermodulation product that you might see. How to find out if this is legitimate, something at the output, or this is just the amplifier itself that might be even slightly overloaded at the input, but you can't change that level. Turn on zoom mode, and it will reveal how many peaks are in 0. If you turn on zoom mode and it reveals 2 peaks, then it will be CPD. If it reveals nothing, there will be no CPD. The other method is to apply a low-pass filter in the return cable, low-pass 40 or low-pass 70 megahertz, which will cut off frequencies above 70 megahertz, getting rid of strong energy of the forward that might be entering the Quiver return input and causing also this effect. Zoom mode you can use for revealing fine details of the peak or ranging very precisely distances. Zoom will show you what is plus minus 2 microseconds away from the marker. So just simply press zoom and it will switch to this picture. Here we've got relatively high noise floor, minus 50 dB. It's high noise floor. When you are searching for low peaks before the return amplifier, then these peaks may be minus 50, minus 40 dBs. So it's more comfortable to work when the noise floor is minus 65, minus 5, minus 70. Sometimes it's just minus 80. When you've got this situation and you are thinking that maybe there is some other peak hidden, you use high noise suppression. That correlation noise floor that we're talking about here can be reduced by accumulating more signal samples and lowering the noise floor. This noise floor reduction can be really like 20, 30 dB, depending on situation and time. It takes a little time, the progress of scans is shown with this blue bar. You can always press button stop to freeze this screen. Then you can press run to run it again. But there is, when you've got the peak revealed on the screen already, there is no reason to wait really until it finishes. You save your time by pressing stop and you've got the record of it. Whatever is shown on the Quiver screen can be saved with save button. It's saved in internal memory. You can pull all the records using a web browser program that needs to be installed on a computer and is available from our website. It's free. When you search for intermittent CPD sources, this will be something that bothers the node at night or periodically and manifests itself as flat elevated noise floor. You go to the fiber node and connect with the Q amp. There is also a trick that if it's okay at certain cable network and you don't have AGC, you can use as well. It's to increase the forward, the downstream level at the fiber node or the RFI node by 3 dB. This will reveal these intermittent sources. In the nodes fed by RFI, you will have higher signal levels and there the CPD sources will reveal themselves automatically much better. So if you are already connected, check if you can see peaks. If you see them, well, you will have to fix them all because you don't have monitoring that would show you which peak is changing its level in the historical records. So you will have to find and fix all of those that are visible. And one of these will be the one that is causing problems. The other may be simply behaving just like that and never reaching very high level for a long time. In the situations that the CW-like interferences are causing noise floor of the correlator go up and hiding low-level peaks, you can change the bandwidth of the input of the Quiver and reveal these peaks from noise. On the next slide, actually this will be a video. You will see how it works. You can see here on the record interference, the CW peak that is, and the other one that they are showing up in the bandwidth between 8 and 16 megahertz. We turn on CPD Radar in standard input band and we see low level of the CPD peak and a jumping noise floor that is sometimes hiding it. For a trained user, this is not a big problem, but sometimes this jumping is much higher. So what you can do, your choice can be narrow adjustable 4 megahertz bandwidth that you can put its central frequency, like here to 30 megahertz. That was between the SC QAMs in a non-disturbed spectrum part. We revealed nicely that CPD peak. Or you can use wideband 5 to 100 megahertz bandwidth. That will actually use the entire bandwidth of your actual upstream. It takes longer to scan because it waits for the moments when SC QAMs are shut down and processes that part of the signal in time domain. The peaks revealed with this higher bandwidth, wider bandwidth, will contain more energy, so they will be indicated as higher peaks, and you can see them. We've changed the scale, and now we can see the peak. For demonstration purposes, we will turn on noise suppression high. That will further increase the scanning time, because after drawing one screen, it will keep processing next and next screens, accumulating the levels. Here you can see that noise floor is reaching minus 60 dB, but the upper blue bar is going, and we see that the noise floor will be dropping below the 60 dB step by step with the progress of the lower blue bar. You can see that this noise floor is getting like ironed. So after many scans, it can reveal the peak from even deep noise. That was everything in the basic training for CPD radar users.